All right, welcome back. We're going to continue to explore properties of integration, especially this last property that's listed on this page, that an integral from a to b can be split up into two integrals, or three integrals, or four integrals, by taking a pit stop in the middle of the bounds of integration. Say we're integrating from 0 to 10, we could equivalently go from 0 to 2, and then go from 2 to 7, and then go from 7 to 10, add those three results together, and we'll get the same total result that we would get if we were to go directly from 0 to 10 all in one step. And one of the reasons that this property is important is that it allows us to integrate piecewise functions, like this one. Say we want to find the integral from 0 to 4 of f of x. For this particular f of x, this f of x is equal to 2x for x less than 2, and is equal to 3x squared for x greater than or equal to 2. So what we would do is we would split integral at 2, and the reason we're choosing 2 is that's where the piecewise function changes its character. I'm going to rewrite this. I'm integrating from 0 to 2 f of x dx plus integral from 2 to 4 of f of x dx, and this just happens to be the halfway point. It's not always going to be the halfway point. For example, if our integral was from 0 to 10, instead of 0 to 4, we would go 0 to 2 of f of x plus 2 to 10 of f of x. So the important thing is we're splitting it where the piecewise function switches. Now in each of these pieces, I'm going to replace f of x by what the correct piece is for that region. In the region from 0 to 2, that's x less than 2, so I'm going to replace f of x by 2x. And then from 2 to 4, the second integral, so from x equals 2 to x is equal to 4, that's going to be f of x is 3x squared, because that's the part that corresponds to those x values. Okay, then each of these can be integrated with respect to x using the anti-power rule. First one gives us 1/2 of 2x, which is 1/2 of 2x squared, which is x squared. This is going to be evaluated from 0 to 2. In the second part, we have 3 times 1/3 x cubed, and the 3 and the 1/3 cancel. We just have x cubed, integrated from 2 to 4, and then we can plug in the bounds. So 2 squared minus 0 squared plus 4 cubed minus 2 cubed. So we get 4 minus 0 plus 64 minus 8, which is 60. That's our answer. Other types of piecewise functions, or other just types of functions in general, the list is enormous, the list of potential functions that we could work with. But an important one that we haven't talked about yet, or much, we talked about a little bit, but not much, is the absolute value function, absolute value of x. Absolute value of x has a v shape. And if we think about this v shape in terms of a piecewise function, the left-hand side of the v shape is a straight line with a slope of -1. So such a function, and that straight line goes through 0, 0, goes to the origin. That function can be described as y equals -x, but only for x less than 0, only for the left-hand side of the number line. As soon as it switches to positive x values, the right-hand side of that v shape is y equals x, a line with a slope of 1 and an intercept of 0. We could put them both together as a piecewise function to describe the absolute value of x function. It's equal to -x for x less than 0 and positive x for x greater than or equal to 0. This allows us to do things like integrate functions involving absolute value of x, and even to take the derivative of functions involving absolute value of x. So I'll show you what the first case looks like. How do you take the derivative of absolute value of x? Well, I'm going to write this as a piecewise derivative. I'm going to take the derivative of -x if x is less than 0. I should be consistent. I'll write 4 for x less than 0, and that's equal to the derivative of x for x greater than or equal to 0. And then I can simplify each one. So the derivative of -x is -1, derivative of positive x is +1, and that's it. That's our derivative. Now this function, this derivative, this f prime, if you were to graph it, has a jump. has a y value of -1 for x values on the left side, and y value of +1 for x values on the right side. And it just jumps abruptly at x equals 0 from one y value to the other y value. It's like a step function. The next derivative that's listed here is the derivative of the ln of x with absolute value around the x. So I'm going to do this one the exact same way. So I'm going to replace absolute value of x by -x for x less than 0 and +x for x greater than 0. So my derivative becomes the derivative of two different things. Ln of -x for x less than 0 and the derivative of ln of +x for x greater than or equal to 0. Now I'm going to use the special derivative rule for taking the derivative of the ln of w. In this case, w is -x, so derivative of -x is -1 divided by -x. So that's for x less than 0, and we get +1 over +x for x greater than or equal to 0. But this can be simplified. -1 over -x is 1 over x, for x less than 0, and 1 over x for x greater than 0. And actually, the log function has a domain problem. Remember, you can't take the log of 0, so I'm going to get rid of this little equal sign underneath the inequality. And then, one more thing is notice that both pieces are the same thing. This is equal to 1 over x for x not equal to 0. And this is one of the reasons that when we talk about antiderivatives of the function 1 over x, we have ln absolute value of x. This is the most general antiderivative. It's an antiderivative that describes the graph of the function 1 over x for negative x values and for positive x values. And the fact that it doesn't work at x is equal to 0 is just a reflection of the fact that 1 over x doesn't exist at 0, ln of x does not exist at 0. All right, so that's taking derivatives of functions involving absolute values. And again, the way that we do those is we split up the absolute value function into a piecewise and take the derivative of each piece, use any rules that are appropriate for each of those pieces. Here's doing the opposite, taking an antiderivative. The function, the first part, 6 times absolute value of x, is the weird part. So most of our attention is going to be focused there. The second part, 3x squared, is not weird, it's just a regular function. So to make this a little bit nicer, I'm going to split the integral up into two integrals. The integral of the first part plus the integral of the second part. I'm not using that integral split property for the bounds yet. I'll have to use that eventually, but I didn't do that. I just said the integral of f plus g is the integral of f plus the integral of g. Now that first integral, I'm going to use the following fact, that the absolute value of x is equal to -x for x less than 0 and equal to +x for x greater than or equal to 0. I'm going to use that fact to split the first integral into two integrals. So this is going to be an integral from -2 to 0. I have to split it at 0 because that's where the piecewise function switches. And I have 6 times -x, because that's what the function is inside the region from -2 to 0, plus the integral from 0 to 3 of 6 times +x dx. And we have the last component there, -2 to 3 of 3x squared dx. So I use the piecewise. And actually, I'll add some more color coding to here. We're splitting it at 0 for the same reason we always split piecewise functions. We're splitting it where the piecewise function switches. In this case, it switches at 0. All right, and now we can take the antiderivative of each of these pieces. Antiderivative of -6x is, well, I'll do it 6 times -1/2 x to the power of 2 using the anti-power rule. This is evaluated from -2 to 0. And for the second part, we have 6 times +1/2 x squared evaluated from 0 to 3. And for the last part, antiderivative of 3x squared is x cubed, and this one's evaluated from -2 to 3. And these evaluations may not be very nice. We're going to have to be careful. So we have -3 multiplied by 0, and then subtract -3 multiplied by -2 squared. Now the 1/2's already been taken care of. 6 times -1/2 is -3. Let's see, and then the second thing, we have 3x squared. So 3 times 3 squared minus 3 times 0 squared. And then we have the last part, 3 cubed minus -2 cubed. And we have to simplify all this. So 0 plus 12 plus 27 minus 0 plus 27. And then -2 cubed gives us -8. We're subtracting it, so plus 8. I'm going to add the 8 and the 12 together. 20 plus 27 plus 27, 54. So we get 74 as our answer. And please double check these calculations and let me know if there's an error. Usually the errors will pop up with the adding and the subtracting, at least for me. Maybe for you too. Okay, here's another type of example involving the absolute value function. This time it's not just absolute value of x, it's absolute value of x plugged in somewhere. In this case, plugged into an exponential. First thing I'm going to do is I'm going to use that same property we did last example. I'm going to split the absolute value of x into 2 pieces. -x for x greater than 0, or less than 0, oops. And then positive x for x greater than or equal to 0. Same thing. Now the integral, both pieces are going to have the 10 in front. We're going to integrate from, I'm going to do the same thing with the colors. I'm going to do zeros on the colors. Okay, so I'm going from -4 to 0. And inside that region, from -4 to 0, it's e to the absolute value of x, and absolute value of x is -x inside that region. And now we have the second part, plus 10, integral, and this time we're going from 0 to +4. Get my color coding straight here. And then absolute value of x inside the second region from 0 to 4, absolute value of x is just x, so e to the absolute value of x is just e to the x. So we just took this piecewise nature of the absolute value of x and plugged it in and broke up the integral appropriately. All right. Now the next step is I'm going to take the antiderivative of e to the -x. We're going to use a substitution. I'm going to let w equals -x. So dw by dx is equal to -1. So dx is equal to -dw. We can rewrite our integral of e to the w times -dw. We get -e to the w plus c. We take the antiderivative, which we can go back as -e to the -x plus c, and we can drop the plus c because we have bounds. That's for our first antiderivative. So there's a 10, and then we found it was -e to the -x. Oh, wrong color. Minus e to the -x. And then this is evaluated from -4 to 0. And then plus, we have 10 Antiderivative of e to the x is just e to the x, evaluated from 0 to 4, and then we can simplify. So we plug in the top bound, negative 10 times e to the 0, subtract the bottom bound, negative 10 times e to the negative 4, and in the second part we have 10 e to the 4 minus 10 e to the 0. Now we have to simplify. E to the 0 is 1, so negative 10 times 1, plus since it's negative times negative, 10 e to the positive 4, and another 10 e to the positive 4, and then minus 10 times 1. And we can finally collect like terms. We have a negative 10 and another negative 10. That'll be a negative 20 total. And then we have 10 of e to the 4s and another 10 of e to the 4s, so that's 20 of those, 20 e to the positive 4. And that's our final answer. And this is not a nice question. This is a very challenging problem. It requires substitution for one of the parts of the integrals. It requires us to split the integral up into two. Requires us to work with piecewise functions. And the numbers aren't so bad, but the rest of it is bad. So I would classify this as a challenging problem. And if you're looking at this saying, oh my God, this is hard, you're right. This is hard. Now here's a better one. This one's better because it focuses on kind of the core feature of these types of problems. And the core feature is just recognizing how the problem can be solved and not necessarily going all the way and finding the antiderivative, which is more mechanical. It's important when you're learning mathematics to distinguish the mechanical part from the conceptual part. And the great value of learning math isn't the turn the crank process that you use to get a number. The great value of mathematics is the problem solving. So this problem really focuses on that component, the problem solving component. We want to transform using the substitution w is equal to 2 times absolute value of x, this integral. And I'm going to do this in stages. The first stage, the simplest stage, is to just, without any thinking, replace each 2 times absolute value of x with a w. Now we have a 4 times absolute value of x, that's going to be 2w. So instead of cos of 2 plus 4 absolute value of x, we have cos of 2 plus 2w. Instead of e to the 1 plus 2 root x, we're going to have e to the 1 plus w. Now we have a part that's going to take more work. We have the dx part, and we have to worry about the bounds. So let's worry about those. So I'll do that down here. Absolute value of x is equal to negative x for x less than 0, positive x for x greater than 0. And what that tells us, this piecewise definition, it tells us we're going to have to split this up fairly carefully. So when I take the derivative, so if w is equal to root x, then dw by dx is going to be a piecewise function. It's going to be negative 1 for x less than 0 and positive 1 for x greater than 0. That means dx is equal to negative dw for x less than 0 and positive dw for x greater than 0. So we need to split our integral up. We need to split it at 0. I'm going to go from, greater than or equal to. So I'm going to go from negative 3 to 0. Well, not necessarily negative 3. We have to worry about the bounds as well. And then the dx gets replaced by negative dw in the first region, since we're going from -3 to 0, so we're in the negative x region. Now the bounds, x equals -3, w is equal to the absolute value of -3, which is 3, so we're going from 3 to 0. And for the second region, we're going from 0 to 6. X is 6, w is the absolute value of 6, which is also 6. So from 0 to 6 of the cos of 2 plus 2w e to the 1 plus w times positive dw. And then we can simplify it just slightly. The simplification process here is just take the negative out front. So negative integral from 3 to 0, cos of 2 plus 2w times e to the 1 plus w dw, plus integral from 0 to 6, cosine of 2 plus 2w e to the 1 plus w dw. And then you would integrate both of those pieces using techniques that we haven't learned yet. So that's why we would stop here, to just transform the integral. I'll fix that w as well. Okay, so I want to go back and break down what happened. The most important part was recognizing we need to split the integral up at 0. And we could have done this in a different way. We could have used the piecewise definition of absolute value of x and split the integral into two integrals that way. But the reason I didn't do that was because the question did not tell us to do that. The question told us to use this as a transformation, to use w is equal to 2 times absolute value of x. Oh, and I screwed something up. What I screwed up is that w is not absolute value of x, it's 2 absolute value of x. So, gotta go back. See, if we had a physical class, someone would have yelled at me. -2, +2. So when I rearrange them, you get -1/2 dw and +1/2 dw in the other region. So I gotta tack those on. See, I need you guys. I need you to be in the room to yell at me and say, "Fix it, fix it. Where'd it go? Where'd the 1/2 go? Where'd the 2 go?" So that would be the correct answer now. So we had to split the integral. When we did the substitution, w is equal to 2 absolute value of x. We can write that as a piecewise function, take the derivative of it. We have two different pieces depending on the x value that we have. That means dx is going to be different in each region. So we have to substitute it in carefully. Right, now that's it for this topic. We'll continue the next topic in another video.